So in class, I mentioned the central limit theorem, and I'm going to emphasize this part again, what I mentioned in class. But then there's some details that we need to cover that I probably didn't have enough time to cover in class. So I'm relying on this video to do so. So I'll read it. In probability theory, the central limit theorem states that under appropriate conditions, the distribution of a normalized version of the sample mean, or sample means, converges to a standard normal distribution. Remember, a standard normal distribution is one of those. So there's the blue one there that's taller and skinnier, meaning the standard deviation's lesser value, where the orange one that's flatter, that is a standard deviation that is a greater value. And the red one has a standard deviation is between the blue one and the orange one, so it's not as tall as the blue one, but also the bulk of it doesn't extend as wide as the orange one. All three of those have the same mean, median, and mode, of course. And the green one has a lesser standard deviation than the blue one, greater standard deviation than the red one, but its mean and median and mode, of course, are less than the red, blue, and orange one. Its mean is somewhere around whatever -2 it looks like, something around there. So again, those are examples of the normal distribution. Here's another example over here, normal distribution. This holds even if the original variables themselves are not normally distributed. So the original population does not have to have a normal distribution. What I've drawn on the right over here on the iPad is this is a right skew distribution, but if I pulled samples from that and took their means, sample means, if I pulled a sample out of that, calculates mean, put another sample, calculates mean, do it over and over and over again, at least generally we talk about between 20 and 30. So taking that sample 20 to 30 times, and I'll get a distribution that is approximately normal, no matter the original population's distribution. So this one is skew right, that one's skew left, this one is a poorly drawn uniform distribution, this one is a Bernoulli distribution. We can also look at all of these different types of distributions. There's uniform again, there's the Bernoulli. This is what a binomial distribution looks like. I've not worked with, or I'm very familiar with some of these. Hypergeometric, geometric, negative binomial, exponential. I've not dealt with that personally, but I've read some things on that. Poisson distribution, log normal, students T, which we'll dig into. Normal distribution we'll dig into. Chi-squared we won't, but it's if you had AP, you would have covered a chi-squared distribution. Maybe not talked about the distribution, but used chi-square as a statistical analysis. And these other distributions, okay? Generally, this is just right skew, that's right skew, and this is slightly left skew, okay? But when we take sample means, we really interested in getting sample means and this normal distribution, okay? And so where did I want to go next? This thing will help us demonstrate what's going on here for those other ideas that come along with the central limit theorem. So this first table, this first interactive table, and again, I'll provide a link. Let me see if I can blow this up and without scrunching the sides too much. Yeah, there we go. That's a little better. Maybe that's easier to see. You can get a little bit more in here. Okay, so what I'm doing here is I'm going to just plot on this graph. I'm not going to. Whoever wrote the software is going to, and the software will do it for me. But I'm going to plot this, each individual roll. So if I roll one die, I get a 1, there it is. Roll a die again, I got a 4, there it is. There's a 3, oops, there's another 4, there's another 1, there's another 5, there's another 1, there's another 5, another 1, another 1, another 6. So this is already sort of not commonplace that I would roll 5 1s and 1, 2, 3, 4, 5, 6, any other number. It almost feels like our die is heavily weighted on the 1, right? Because almost half of them were 1s, and the other 5 numbers are giving me only 6 outcomes. This is just randomness, right? Or as random as we can get in, as a human. If I continue to do this, the others will fill up, and eventually It might take a while, but eventually the distribution will be a uniform distribution. How do I know that? Because the probability of each of these numbers getting rolled on a single die roll are equally probable, right? They're 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Now, how can I hasten this? Because this is going to take a while for me to catch up to that now 20 rolls of 1. So if I roll, I'm going to roll 1,000. But if I can roll 5 dice at a time, that I'm still counting them as individual rolls. I'm just rolling 5 at a time. So if it comes up 2, 3, 6, 1, 4, I'm going to record a 2, a 6, a 3, and whatever I said. I don't remember. So there are 5 more rolls, 5 more rolls, 5 more rolls, 5 more. So here comes 5 more rolls. And look how it's catching up. And if I just did 1,000 rolls, even if I just did it once, that looks so much closer to a uniform distribution, right? And it remains so because I rolled it so many times. This should make sense to you, right? Because we did this in class, we've talked about it, and we kind of know this is what should happen if I did enough rolls, okay? Now, I'm going to scroll to this next part of this. I should clear this. It's some leftover stuff from when I was playing around. I'll put this here in case we need to go back and refer to it. So this little second section, again, you can link and play with it yourself. Instead of just rolling 1 die, let's roll 2 at a time. You can use the graph and buttons below to simulate this. The graph will record not the individual rolls. So if I rolled a pair of die, I'm not looking at a pair of die as in I'm going to get a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. That's not what we're talking about here. We're not playing Parcheesi. I am rolling 2 die at a time, and I'm not recording each one as 1 or 6, meaning I won't get 2 rolls out of this. I'm calculating the average. So I'm calculating the mean. So this is a sample. This is simulating a sample of 2. I'm going into this population. Notice how that population is uniformly distributed, right? This rectangle, right? The population is a uniform distribution. I'm going to roll a pair. I'm not counting them as individual. I'm taking a sample of 2 die rolls out of here. If I pulled a 3 and I randomly pulled a 3, then I'm going to take the average. It will be 3. But if I randomly pulled a 2 with a 6, 6 plus 2 gives me an average of 4. So this distribution, and I'm going to plot a 4, this distribution is going to be a plot of the sample means or the sample averages. And so I'm going to roll 1 die. I'm going to roll 1 pair of dice or pair of die, whatever, however you want to say it. And I get a 4.5. So that must have been like a 5 and a 4, right? There are probably multiple ways to get a 4.5. I'll show you how you could calculate what those possible rolls are, not that it matters to you. So if it was a 4.5, that would be the roll of 1 die plus the roll of the other die divided by 2. So whatever the combinations are of A and B that could roll a 9. So it could be a 6 plus a 3. It could be a 5 plus a 4. It could be a 4 plus a 5 if we treat each die separately, or a 3 plus a 6, right? Those are the 4 combinations that would give me a 9. Yeah, because I can't get it. If I rolled a 2, there's not a 7, right? So there are 4 of those combinations. Doesn't matter unless you wanted to calculate some sort of probability. What's the probability of getting that? Blah, blah, who cares? Or I don't, specifically. So I'm going to roll another pair. I'm going to take those 2 numbers, those 2 die results, add them together and divide by 2 to get their mean. And I got a 2. Okay, so there are fewer combinations for the 2, I believe. Yeah. Because 2 is just 1 and 1. I can't get another, not 1 and 1. 2 and 2, 1 and 3, 3 and 1. Or the other 2 and 2 if you can treat them separately. I'm going to roll it again, and I'm going to start filling this thing up. Except, according to what the Central Limit Theorem tells us, we should not get a uniform distribution. We should get a normal distribution. You saw in the Wikipedia article, you may have, I don't know if you noticed, it calls this Gaussian distribution. That's another name for a normal distribution is Gaussian. Now again, I could roll this one over and over and over again. It's going to take me a long time to fill this in. I could roll 5 pairs at a time, and all the software is doing is if I rolled a pair, calculated, plotted a point, rolled a pair, calculated, plotted a point, rolled a pair, calculated, plotted a point. Do that 5 times. I'm just rolling it 5 times in a shot instead of 1, 2, 3, 4, 5. So there are 5 placements. There are 5 more means, 5 more means, 5 more means. Again, it's still going to take me a while to build this up. If I go 20, it's going to still take a while. I'm just going to roll 1,000 straight away and boom. If I do this a bunch of times, does that start looking like a normal curve to you? The lowest number down here is a 1. The highest number up here is a 6. Because those are the 2 numbers that I could get averages, right? In this situation, my sample has an n of 2. N equals 2. So the sample size is 2. Sample size is 2. N equals 2. Then I can take a whole bunch of samples. Okay? Okay, next. I went and bought a pack of 25 dice. Okay? And I'm going to roll all 25 at a time. So instead of 2, I'm going to roll 25. And then I'm going to take all 25, add them together, and then divide by 25. And I get 1 data point, an average of 3.88. Okay? 3.88. To calculate the different combinations of that, it would be crazy, right? 3.88 must be A plus B plus C plus, and then I'd have to get out here at 25. I would have to get to Y plus, U, V, W, X, Y. I wouldn't go to Z because that would be 26 letters, right? And divide this by 25. I'd have a whole bunch of different combinations with those numbers coming out. There's no, I don't think there's a reasonable way for me to figure out what the various combinations would be, okay? But I don't really care about that. I just thought it was an interesting thing to yap about. So again, I can roll another 25 and get another data point. Each time I do this, I'm going to get 1 data point, which is the mean of the roll of those 25. I can do 20 or 5 more times at a time. That's all the software is allowing me to do. Or I can do 1,000 at a time. And notice that I'm getting this normal curve. But also notice that this normal curve, it's down here a little bit, right? There's some data points down there, and there's some data points up here. Conceivably, there could be a data point up here. I'm scrolling across it. It doesn't look like I'm getting anything. Okay, doesn't look like I'm getting much, but there could be one over here. There's nothing preventing it from happening. There's nothing preventing a 6 from happening, but all 25 die would have to come up 6, yes? So that's more improbable than 2 of them coming up 6. So that's why the probability of that happening is significantly lower than, and equivalent to rolling a 1. So what ends up happening is I get this normal curve, and notice how the normal curve is not as wide as this one. Okay? The standard deviation of this curve is less. The standard deviation of this distribution, I should say, is more. Standard deviation is less. Standard deviation is more. So when I increase the sample size, the standard deviation decreases. It gets skinnier and taller. In another textbook and author, he kind of describes it as if you take hopefully you know what maybe you don't, a table runner. That's what he used. I think of it as a tablecloth, a skinny tablecloth. But a table runner is like this white thing here, this lace. It's this thing here. It doesn't cover the whole table. It's just this here, right? It's just this thin thing that doesn't cover the whole table like that. So imagine you're sitting at the table like that, and you put like a dowel, a piece of wood, a metal bar, a broom handle, whatever, but cut the broom off because that's all clunky. Stick the broom handle underneath in the middle here, like goes across here. And imagine lifting it up. If I lift it up, yeah, it's going to be a little bit pointier than the normal curve is, but imagine if I start lifting it up, when I lift it up here and I lift it up a tiny bit, over here it's going to lift up as well, right? And over here at the end it's going to lift up. It's going to start lifting up when we remove that bowl, right? And the tablecloth will start pulled towards the inside, towards the middle. And as I lift it up, this whole thing lifts up because there's like a bump here where the bar is, and it extends probably not to the edge, but closer to the edge. Then, if I continue to lift it up, the weight of the fabric itself will pull it in towards the middle, And so what was once only touching the table out here on the edge, that point slides to the inside because the fabric has to also pull in the inside to accommodate up going up. So it's sort of simulating like the fabric will pull, the runner will pull towards the middle as my my broom handle goes up. That's kind of what's happening here when you try to visualize this, right? Here's the bar, here's the tablecloth drooping down and touching the table. When I only lift it up a tiny bit, it extends over towards the edge of the table on both sides. But as I continue to pull this bar up, it gets taller and pulls towards the middle. That's a way to think about it. The next section is me actually increasing the sample size from 25 to 400. And so once I roll 400, I don't have 400 data points. I have one because I'm taking the mean of those 400. Pow, one data point. Pow, one data point. Pow, one data point. Pow, one data point. But again, 5, 20 at a time, 100 at a time, but more quickly get the image, 1,000 at a time. And notice once again, when I increased the sample size from 25 to 400, my distribution gets more narrow, or said in a more statistical way or more mathy way, the standard deviation decreases once again. The standard deviation of this curve decreases from when it was 25. So as I increase the sample size, I decrease the standard deviation. Okay, all things else being true. Okay, those are some of the nuanced ideas that come with the central limit theorem. If you got the idea, you can stop. But I'm going to play around with this other simulator, maybe cut it out or whatever. We'll see. So I'm going to refresh it. We want an exponential distribution, let's just say. Last time we used a normal uniform distribution with die. This is just telling I can use any distribution I want. And I want to go show you this. So I just chose exponential. So it looks like this. The distribution I'm using right here of the population is that. So even if I use an exponential distribution, if I choose a sample size of let's say 2, okay, and I'm going to take 1,000 samples. Here are the 1,000 samples coming out, and this is not very approximately normal, right? It's not so much because you can still see it's right skewed. But notice how there's this curve downward over here. And if we look at, I think it was this one. Yeah. Look, there's no curve downward. So the distribution of the sample means is not going to give us this distribution. It gives us this. But what happens if I increase that sample size from 2 to some other number? Can I decrease? Because I want to clear this. Okay, so I got exponential and 1,000. So let's change this to exponential. Let's have the sample size of 30 instead of 2, and I have 1,000. So if I run it again, notice my distribution looks, or is much more closely approximating a normal distribution. And then if I use the same criteria but increase the sample size to 300, what we're going to see is a normal distribution, but it will have a lesser value or a smaller value. I prefer to say lesser value for its standard deviation, meaning it's going to be more narrow. And here it is, more narrow. Okay. I guess we could look at the actual standard deviation. Here's 0.0572. 0.0572. 0.0572. The first one was just sample size of 2. We have a standard deviation of 0.7. Okay, so let's bump it to 30. And we'll get, this is the first time we got a more normal looking distribution, and the standard deviation is 0.17. Then I crank this to 300, right? And then we get 0.057, I think we got. This one we got 0.0582. Okay? So the standard deviation decreases, I increase the sample size. So sample means, the mean of repeated random samples taken from a population. Those are sample means. That's what we're plotting in this thing here. The sample size, the number of observations in each sample, n. Generally, the CLT, Central Limit Theorem, begins to apply when n is greater than 30. That's why we weren't getting a normal distribution with the sample size of just 2. Okay? Though this may vary depending on the underlying distribution. Remember, so like if we started with a normal distribution, we may have gotten something that was more normally distributed or more closely approximated. Blah, 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 blah. Okay. All right. So that's it. So maybe the second simulation was more effective for you to see. And we get the actual standard deviation and the mean out of it as well. So